So what I'm going to be talking today is about data efficient deep learning using physics-informed neural networks. And I think it's better if I focus on a single application, go into a lot more details that I usually go in my talks. So that's about the brain aneurysm of a patient, which could rupture, and this could be life-threatening. And what are the treatments for an aneurysm these days? You can do open repair, which is basically you remove the aneurysm. You can do a stenting, put something where the aneurysm is living in. And by the way, I cannot see the chat. So at any time, if there are any questions, please feel free to stop me and ask questions. But I don't see the chat. I'm going to need some help. So what are the treatments? Open repair, stenting, coiling, and clipping. But how do doctors decide these days to do a surgery or no? There is this Hunt and Hess scale. It's from around 1960. And it says at level 1, if there is asymptomatic or mild headache, probably there is no need for a surgery. If there is moderate to severe headache, the likelihood of the patient needing a surgery increases. And then the last one is the patient being in deep coma. But this is from 1960. Can we actually do better? We are in the 21st century. Can we actually do better? So that's going to be the topic of this talk. I usually give a talk on hidden physics models. The talk is available online, so I'm not going to do that anymore. But that's about a series of papers that we have been working on over the past few years, under the umbrella of physics-informed machine learning. Let it be neural networks, let it be Gaussian processes. But today I'm going to be focusing on this paper. It's about hidden fluid mechanics, and it's exactly trying to address the problem that I just explained. What I'm not going to be talking about today is about convolutional neural networks and images. It's not about language, and it's not about generative adversarial neural networks. But why am I including this slide here? The reason is there is physics even in our images. There is inductive bias. If we take this car, shift it to the right, left, up, or down, it still needs to be classified as a car. And maybe because convolutional neural networks are sort of invariant to these sort of translations, maybe that's why convolutional neural networks have been successful. A similar story is about language. Maybe the sequential nature of the language is something that we can build upon. People started with recurrent neural networks because at that time, we didn't have enough data to train giant models like transformers used in GPT or BERT these days. But the more data you have, the less assumptions you need to make about your system. Because the more data you have, you can actually learn those inductive biases, the physics of the problem from your data. I have this course. It's Applied Deep Learning. It's a 2-semester long course on all of these topics, at the ones that are relevant, that have an impact. Let it be in computer vision, let it be natural language processing, multimodal learning, when you combine images and text, generative adversarial neural networks, variational autoencoders, speech, reinforcement learning, graph, recommender systems, and computational biology, or AI for science. What I'm going to be talking about today is going to be related to 3D, because we have a 3D geometry, and it's going to be related to AI for science. But the course is available online if you're interested in other topics in deep learning. So let's go back to our problem. The problem is about the aneurysm behind somebody's eye. This is the input data. You do 4D MRI or CT scan of the patient. Basically, you go to your radiologist, they're going to inject dye in our arteries, and they're going to do their imaging. In the end, what you're going to get is going to be a video. It's a 3D video. That's your input. And you want to design an algorithm that takes this image as an input, and it's going to output the corresponding velocity inside the aneurysm. And as soon as you know the velocity and the pressure, you're going to be able to compute shear stress. So this is going to give the doctors more information, more quantitative information of how severe this aneurysm is. What are the likelihoods of this aneurysm rupturing? So that's the input data. This is the output from the algorithm. So the input, let's take a look at it. Let's take a closer look at the data. It's going to be a point cloud, and it's going to be time dependent. So it's going to be a set of points in a space and time. For instance, at this point in time, at this point in a space, X, Y, and Z, you know the corresponding concentration. You can think of this similar to black and white type of images. For instance, you can think of this as MNIST. The color is going to be a value from 0 to 1. So we have T, X, Y, Z, and the concentration. And then we have a set of these points. These are the measurements. The output of the algorithm, what we expect out of it, is again a point cloud. It's going to be time dependent. And then you want to know at this point in time, at this location in the space, what is the velocity, u in the x direction, velocity in the y direction, velocity of the blood in the z direction, and the pressure. And as soon as you know that, you're going to be able to compute shear stresses on the wall of the aneurysm. So that one is a post-processing. If we solve this problem, the other problem is solved. And we want to do deep learning. Let's put our deep learning hats on and take a look at the methodologies that are currently available and try to perhaps use one of them and see whether it's going to be successful or not.
Maziar,
Yes.
there's a question, and possibly it's better to clarify the question now. So the question is, where do you get the pressure from when using non-invasive diagnostic imaging?
That's a great question. And that's about the data. Where do you get the data? And actually, the entire talk is about that. How do you get the pressure? How do you get the velocity? But for the sake of illustration, you're right. If this is a real, the geometry is real, but if this was data coming from a real patient, you wouldn't know the exact ground truth for you to be able to compare. That's why we had to go back to simulations. But things are going to become more clear as I move forward. So let's try to solve this problem using existing deep learning techniques. How about using, somebody might say, 3D convolutions? we know that we can put a box around this 3D object, voxelize it. Voxel is similar to having pixels. But if you do that, there is going to be a lot of white space or empty space. So maybe using 3D convolutions is not a good idea because it's going to be wasteful. That's why people came up with the idea of PointNet. I'm actually going to show you what PointNet is. But then somebody else might say that there is a newer version of PointNet. How about PointNet++? Let's use that. And another person might say, you can represent your mesh or your data using nearest neighbors, create a graph out of it, and then use graph convolutional neural networks or dynamic graph convolutional neural networks, DGCNNs. But before we dive into choosing a method or a model, let's take a closer look at the data. And this goes back to the question. What is the data? This is the input data. For that particular patient, you had T, X, Y, Z, and CI. And this is a set for that patient. Then you somehow know the corresponding ground truth. Maybe you get it from simulation. Maybe you have it from expensive 4D MRI. Actually, from 4D MRI, I have a colleague here that we are working on some real data, and then you have the corresponding velocities. Maybe you don't know the pressure, but you know the corresponding UVW. But for now, let's say this is your data. Somehow you obtained it. But not only you need to have it for this particular patient, for this particular geometry, you need to have M of those. M is the number of data that you have. M is the number of different patients. And this is going to be your training data. So you are going to have a set of sets or set of points. As soon as you have that, hopefully you have that, you're going to be able to train a PointNet. So this is the architecture of the PointNet. It's a famous type of a neural network. It takes as input a point cloud. And if you're interested in a classification task, which we are not, it's going to give you K classes. So we don't worry about this part. Our task is a regression task. Maybe we can borrow ideas from semantic segmentation. So maybe this branch of the network is relevant to us. N is the number of points in one of these sets, which could be different from one patient to the other. The original PointNet paper has 3 inputs. In this case, we have 1, 2, 3, 4, 5. And the output of PointNet is going to be the same number of points in your point cloud. So it's going to be corresponding to T, X, Y, and Z. And then you have M of those. M is going to be, in this case, 1, 2, 3, 4. So you're outputting U, V, W, and P out of PointNet. But the architecture is very simple. What it does, let's forget about this input transformation, which is just a change of coordinates. It takes a point, pushes it through a neural network. It takes you from dimension 5 to dimension 64 to dimension 64, and it's going to give you n points in 64 dimensions. But then it's going to do the same thing. It's going to be the same weights and biases, and you are processing each point independently. You do another transformation, change of coordinates, and then you keep doing the same thing. You take your points, push them one after another through your MLP, multi-layer perceptron. In the end, you want to extract some global features from your geometry for this particular patient. You just average these out, or you take a maximum pooling. It's a global maximum pooling along this dimension, and that's why the dimension n disappears. It's going to give you a very long vector. You take that, you broadcast it here from a layer before, you just copy and paste. You do the same thing, take your points, push them one after another through a bunch of MLPs, which are sharing parameters. And then in the end, output your velocity and the pressure. Okay, perfect. Now to train this, we need to have millions of patients, millions of geometries. But we are dealing with a small m problem, small data problem. Why is that? And what is the scale of m that we can hopefully find? It's not even in the order of thousands. It's going to be in the order of 100. So it's not enough to train a point net. So we have a problem here. We need to deal with the small m problem. Okay, let's put back our deep learning hats on. Come up with some ideas. Somebody might say, if you don't have enough data, don't use deep learning. That's not the correct way to go about it. Use classical scientific computing if you can. And actually, we are going to try to do that and see if it is possible in the future slides. Maybe use other type of machine learning algorithms, maybe do linear regression, maybe do Gaussian processes. But we really need this is going to be a complex flow, the velocity inside the aneurysm. And we really need that function approximation properties of deep neural networks. So we really need that. Let's see if we can get around this small m problem. Somebody might say, collect more data. Maybe wait for the technology to evolve so that you have fancy MRI machines that are going to give you more data faster. Even if you wait a few years to collect more data, you still have a problem. This is a medical field, and in medical fields, there is this idea of privacy. Maybe the patients are not willing to give you the data because this is their medical record. They don't want to share it. Okay, to deal with the privacy concerns, there are also ways of dealing with that, maybe doing federated learning. And the idea of federated learning is that rather than transferring data over the internet, you can actually transfer the gradients of a loss function with respect to the parameters and transfer those, just transfer the gradients. That's an idea. Somebody might say, in the case that you have a lot of input data, maybe that's cheaper. Maybe you can use CT scan. Maybe you can collect data that are unlabeled. You don't know the corresponding U, V, W, or P. And then you do unsupervised, self-supervised, or semi-supervised learning. The type of ideas that you see in natural language processing for training GPT or BERT type of models. You first do unsupervised and semi-supervised or self-supervised learning, and then you do transfer learning. You transfer whatever that you learn from that exercise to this particular problem. That's an idea. Another idea is to use simulated data. Maybe it's expensive to collect real data. How about going about this problem by collecting simulated data? And actually, this is a promising idea. We are gonna pursue that and see, is it gonna solve a problem or not? And one argument against using simulated data is that you're gonna end up with something called reality gap, that the simulated data is gonna have a different distribution compared to the real data. There's gonna be a gap between the distributions. And to deal with that, there are methods like domain adaptation or domain randomization type of techniques. Even if you manage to do all of those, there is going to be the question of trust. Are you really going to trust the predictions that are coming out of a neural network to do a surgery on somebody or no? How much do you trust that? Even if you trust it, is it going to be robust? We know that neural networks are sensitive to adversarial examples. Maybe there is an adversary shifting the input a little bit and then causing a patient to go through unnecessary surgery. Let's go back to that idea of simulation. That's promising. Where else do we see it? We see these sorts of ideas in robotics. When you want to go and work with a real robot in the physical world, it's going to be more expensive, much more expensive to collect data. How do people deal with that? They collect data in a simulation, in simulated environment, like OpenAI Gym, and they do domain adaptation. You see the same techniques in self-driving cars. You can sit in a car or let the car drive itself, collect data from a left camera, center camera, right camera, perhaps a couple of LiDARs, collect data, store them, and then work with them. But that's dangerous. You cannot put a self-driving car on the roads on its own. It's going to be expensive to begin with, and it's going to be really dangerous. How about collecting data in a simulated environment and then do domain adaptation? So now somebody might say, if you're going the simulation route to collect data, how about doing simulation only once? You extract the geometry from a patient, you mesh the geometry, and meshing, for those of us who have been working with meshing, we know that you need to have an expert in the loop. It's not only a science, it's also art of how to come up with conforming meshes. And so you need to have an expert in the loop. Even if you do your meshing, you can do your Navier-Stokes solver, your favorite one, maybe use OpenFOAM, maybe use Nectar++, etc. And this is gonna solve your problem. Basically extract the geometry, mesh it, run your Navier-Stokes, and it's gonna give you the flow inside the aneurysm. Perfect. But there is a catch. The question is, what are the correct boundary conditions? What boundary conditions are you going to use at the inlet and the outlet? To see the complexity, this is the aneurysm behind the left eye of a patient. You're cutting it from the entire arterial system of a human being. Yes, Navier-Stokes equations, they are based on first principles, like conservation of mass momentum. but the boundary conditions that you're going to choose, they're going to end up being really ad hoc. Somebody might say, treat this as an inverse problem. You have this data. Now your problem is to adjust your boundary condition at the inlet and the outlet. You keep adjusting it, and you keep doing multiple rounds of simulations so that the flow is going to give you this pattern in the concentration. So you keep adjusting, back propagating your errors so that your forward simulation is going to match this pattern. But let's see how many hours you're going to need to do that. Even if you have your mesh in place, running this Navier-Stokes solver is going to take you 48 hours for one forward simulation. To solve the inverse problem, you're going to need to solve the forward problem thousands of times. So it's going to be thousands of times 48 hours to give you a solution to this problem. And this is certainly beyond my lifetime, or my patience. So this route, we are not going to go, the scientific computing route. The deep learning route didn't work. The scientific computing route is not going to work. But fortunately, we were working on these ideas of physics-informed deep learning for a couple of years. And we were trying to devise a framework that you can use it to solve forward problems, inverse problems, data assimilation type of problems, and model discovery problems. So a wide range of problems. And our problem is going to be related to the inverse problem that we are seeing. But what is the observation? What is going to be the physics here? The physics is going to be written in the form of differential equations, partial differential equations. And there is this key observation that the derivative of a neural network is another neural network. These two neural networks are going to share parameters. They're going to have the same weights and biases. The activation function changes. Maybe if you're using tan h, it's going to become 1 minus tan h squared. Basically, the derivative of tan h is going to be your activation function. The weights are going to get transposed. But in the end of the day, what you're going to end up with is still a neural network. It's going to have a computational graph. And why is this observation important? Because a lot of partial differential equations, you can write them this way. It's going to be ut, if it is time dependent, is equal to a nonlinear function of time x, the solution. You are taking derivative of the solution with respect to x twice, etc. So that's a generic form. These derivatives, we are going to compute using automatic differentiation. These are going to be neural networks. This is going to be another neural network. Based on this observation that the derivative of a neural network is a neural network, you create a physics-informed neural network, F, and then you fit it to the data that you have. Some data are going to be on your solution, and some data are going to be trying to enforce F to be 0. And let's take a look at these classes of problems. For the forward problems, you know your N exactly. So you know what your N is going to be. And then you just give it initial and boundary conditions as your training data. And you solve this minimization problem. For inverse and data assimilation, you know your N up until some parameters. Or maybe you have observations on if U is a vector on only one of the components of your vector. For model discovery, you can actually say N could be a neural network, or if you want it to be explainable, you can say N is a linear combination of maybe polynomials or sines and cosines. And then you can discover your physics, given enough data. And there are two arrows. One goes from left to right, the other one from right to left. Unfortunately, if you have small data, you cannot learn your physics. You have to make some assumptions. That's just a fact. So let's try to use that for our problem. Previously, PointNet was using fully connected neural networks, MLPs. We are going to use that. We had time, X, Y, Z, and the concentration as the input. And our neural network was outputting U, V, W, and P. We are going to make a slight modification. We take C as the input. We put it as the output. And these sorts of ideas, you see them when you're doing deep Q learning for reinforcement learning. You take your input, put it as the output. Okay, so far so good. Now this gray box is very boring. There is nothing special about it. But the catch is you have data only on this variable, on the concentration. You have no data on U, V, W, and P. To compensate for that, you know your laws of the physics. You know conservation of momentum, E2, E3, E4. You know conservation of mass. These are first principles. And then you have an equation for the concentration, which is being advected by the flow. It's being pushed by the flow, and it's diffusing. So this is the diffusion coefficient for the concentration, and the Reynolds number is related to the diffusion coefficient for your fluid. And you don't even need to know what is the Beckler number, what is the Reynolds number. This could be two additional parameters on top of the parameters of your neural network that you're learning. E1, E2, E3, E4 are E5 are gonna end up being physics, informed neural networks. They're gonna share the same parameters as this gray box. And the cool thing is, you don't need to have data on E1, E2, E3, E4, and E5. You don't need to have labeled data because the label is going to be 0. You have some data on the concentration. This is 1-point cloud. And then you are trying to satisfy your equation. Equation 1 being 0, equation 2 being 0 up on some collocation points. So it means that you can have infinitely many points here, as much as you want, because you don't need to pay the labeling cost. Once this minimization is done, you're going to end up with your flow. What did we just do? We collected 0 external data. This was 0 training data. Basically, M, that capital M is 0. And we are only testing our algorithm. So there is going to be an optimization when it comes to inference, when it comes to the testing. So we had only 1 data for testing. That was from scientific computing perspective. Why do people in deep learning should care about this or these sorts of first principle type of thinking. We had a speaker from Google the other day, and he was trying to solve this task. It's a video prediction task. Given the previous frames, predict the next frame. That's a task. And we know that in deep learning these days, they try to solve the problems by collecting more data and training larger and larger models. So they had a small model, they had a big model trying to predict the future. Let's see what happens. In the next frame, the predictions are fine. In the frame after it, the short of this person is changing color in both of the models. The smaller model is losing the leg of the person. And the identity of this person is turning from a man to a woman. We keep predicting. This other neural network is losing it. The person is disappearing. In the next frame, it disappears totally. Now the smaller model is gone. The person disappeared, and that one is turning into a woman with a different color for the short. Let's predict more. And then the clothing of that person changed again, even from the biggest model. So how about this? We know that a pixel, there is going to be this idea of conservation of pixels. A pixel is not going to appear or disappear out of nowhere. It's just going to get transferred from one location to the other location. This could be the physics for this problem. And perhaps it can solve the problem. And we were using it. We were using conservation of mass. Mass is not going to appear or disappear out of nowhere. It's just going to get transferred from one location to the other location. And that was our continuity equation that we were using. I think I will go through the source code for this, the topic that I just explained. And the source code is going to be HFM, hidden fluid mechanics. There's going to be some utilities. We needed to do forward gradients rather than backward gradients because we had more output variables compared to the input variables. We know that backpropagation is useful when you have maybe a loss function, which is only one output variable, and a lot of input variables like your weights and biases. So that's useful in that case, because in one shot, you're going to get the gradient with respect to every single parameter in your model. But in our case, we were going from low dimension, maybe time X, Y, and Z, to more variables, concentration, U, V, W, and P. So we had more variables at the output level. So there is this trick that you can use. You can do forward gradients by calling backward gradient twice. It's going to be as efficient as doing a forward gradient yourself in TensorFlow. We are going to define a neural network. You're going to have a set of weights and biases and some gammas. It's a callable class, we can call it. We couldn't use batch normalization. We know that for a lot of neural networks to train, you need to do batch normalization. We couldn't do it because batch normalization is going to interfere with the physics of the problem. It's going to interfere with the gradients that you're taking. So we didn't have that luxury, so we said we are going to use weight normalization. We couldn't use ReLU activation function. We decided to use swish activation. It's a smooth approximation to ReLU. We know that ReLU is an important contribution for deep learning. in general. It didn't work for us because we are taking derivatives of our functions with respect to the input, and it's going to interfere with the physics. If, let's say, your problem is doing a regression on a sine function, the red dashed lines are going to be the regressed function. The first derivative is perhaps fine. You're going to have some noise, which is perhaps going to mess up with some of your first order derivatives, but maybe you can live with that. But the second order derivative is just going to zero out. So we couldn't use ReLU because we know that there is second order derivatives in the Navier-Stokes equations. And if you kill them, then they are not going to be Navier-Stokes anymore. So you create your neural network, which is going to output concentration, U, V, W, and P. This is exactly the figure that I showed. Then we are going to call forward gradients 7 times. And then we are going to collect. This is our concentration, the derivative of the concentration with respect to X, Y, X twice. And then we are going to return our equations. These are Navier-Stokes. What else? For TensorFlow, you need some placeholders. This is where the data is going to go in. So that's not important. You create your neural network only once. This is the gray box. You're going to call it twice on 2 sets of placeholders. So it's the same neural network, same weights and biases. You just call it twice. And then you're going to do your Navier-Stokes function, which is going to return your equations. And your loss function is going to be, you have some data on the concentration. You just do mean squared error on those. For your equations, you don't need to do any labeling. Your right-hand side is just 0. And then you do mean squared error. You set a learning rate, you set your optimizer to be Adam, and then you do your minimization. You set your model. The Peclet and Reynolds number, you don't actually need to set them. You can actually learn them. You train, and then you do your prediction. These are the predictions of your model. These are the relative L2 error in space. And we know that our problem is time dependent. So this is the errors that you're making. For concentration, it's boring. There is nothing special. But the velocities are coming out of the neural network and the pressure. So you had no data on them. So we had this reviewer of our paper asking us to do systematic study with respect to the resolution of a point cloud. We are using a single point cloud, but how sensitive are you to the resolution of your point cloud? What if you have 201 time steps and 15,000 points in your space? What if you reduce the number of points in the space from 15,000 to 10,000 to 5,000 to 2,500? What if you reduce the resolution in time? What if you do all of them together? Reduce the resolution in space and time. What's going to happen? How sensitive is your algorithm to that? And when is it going to break? At that time, I was at NVIDIA. I had a DGX2 machine in front of me. So I said, I'm going to fire up 16 GPUs with different noise, with different resolution. Run all of them. And at some point, the algorithm is going to break. And we're going to report failure cases in the paper, and the reviewer is going to be happy. This is 2,500. We are here, and the algorithm didn't break. So I had to fire up 16 other GPUs. to break the algorithm. And at some point in the second exercise, it broke, where you have around 13 time steps and 2,500 points in your space. There was another request: study the robustness of your method to noise and keep adding noise. 1%, 2%, 3%, 20%, 40%, 60%, 80%, 100%. And at some point, it's just pure noise compared to your signal. And the algorithm, you can see it's not breaking. It's acceptable relative error in all of these variables. To do that exercise, I fired up 16 GPUs, hoping that it's going to break after adding 30% noise. It didn't break. I had to do another round. It didn't break. Another round, another round, another round. And the algorithm didn't break. I gave up. Why is it data efficient? Not only we are being data efficient in the number of observations, so we have only one observation for one particular patient. We are also efficient in the number of points in the point cloud. And we are also robust to noise, exactly because of the physics of the problem. So many of the functions are not going to happen. They are just not physical. There is this nice observation that a constant is a solution to Navier-Stokes. So these are the trivial solutions. These are the obvious local minima of the optimization. And we can actually see that during training. The loss of your concentration, you have data on it, so it's going to keep going down. But your equations, they're going to start from very low. They're going to jump up, and then they're going to go down. So they're going to escape the local minima. Same thing is happening here for the other equations. We were doing internal flow. You can do external flow and compute interesting things like lift and drag forces. This is my last slide. And the next one is future works. What is the ultimate goal of machine learning these days, and deep learning in particular? It is to come up with an algorithm that performs the best on some test data. And we usually don't care about the cost. Maybe it's time to start thinking about the cost. And how does it compare to statistics in general? The goal of statistics is to come up with a model that explains the data. And these days, there is this new emerging field of explainable AI trying to be somewhere in between the two. But let's take a closer look at the problem that machine learning is trying to solve. That problem seems to be ill-posed. Why is that? We are looking at a performance metric, for instance, accuracy. And you can see that every single day, there is a paper coming and saying that we are pushing the state of the art. We are getting higher level of performance. It means that there exist many algorithms that are going to give you that level of performance and above. That's just an evidence. Let's forget about choosing appropriate metrics. What are some of the other interesting questions? Are you really coming up with the simplest model that you could come up with? Are you using the least number of parameters? Are you using the least number of data that you can? And maybe it's time to start thinking about the Occam-Brazer's principle again, that we are looking for a model that explains the data, that fits the data. At the same time, it is the simplest model that we can come up with. Questions such as how many training data are you using? How many of them are labeled? How many of them are unlabeled? How many validation data are you using? Can you reduce the number of data that you're using? How much energy are you spending on training your models? How many GPUs, TPUs, CPU hours are you spending? Can you explain your model and its predictions? Is your model robust to perturbations and adversarial examples? These days, we are using more and more training data. We are increasing the sizes. There is a chance that our test data is going to end up being a subset of the training data or very similar to it. Are you just memorizing your data or no? How about the corner cases? If a car is driving on the wrong side of the road and your model is making some predictions on that data, should we just brush it off as an outlier? Or it's actually telling us something about our model? And I think I'm going to stop here and answer questions.
Thank you very much, Maziar, for the introduction to your work and also to outlining the future direction, because there are several questions actually going in the direction of the future works that you have outlined. But maybe we can start with coming back to the first question that was raised on where do you get the data from? And maybe now you can explain if you ever got data from real patients, or was it just simulation that you waited?
So let's go back to this slide then. For this particular problem, because you need to know your ground truth, and the ground truth may be the velocity you can get, and it's going to end up being very noisy if you do real data, but the pressure you're not going to get. Okay. From real data, you're not going to get that. But now you want to prove a concept that if you know your physics, and if you assume that your physics is correct, is your algorithm actually going to give you back the corresponding velocity? And the answer is yes. For that, you need to work with simulated data.
And there's also a related question to that. You mentioned that you were just using data from one patient. You were simulating the case for one patient. But did you also validate what happens if you transfer it to a patient with slightly different characteristics? So how transferable is the model that you trained?
Well, yeah, absolutely. So what you can do in this stage, if you have a new patient, you can warm start these parameters. So you don't have to start from random weights and biases. You start from weights and biases that are good for the previous patient. And then there is going to be this learning happening on the fly.
Okay, so you would not take the trained model that you adjusted to the data from one patient and apply it to another patient, but rather start with a pre-trained model and then adapt the learning to the data of that patient.
Yes, so it's going to be the idea of fine-tuning.
Okay.
Actually, if we had more data, if we had some training data, then that would be the perfect scenario for us. Why? Because you still can put these constraints on your data for different patients and do your training, maybe train a point net. But the problem was at that time, we were in academia. And once you're in academia, it's very hard to have access to data and compute.
Okay. Thanks for the answers. There's again a bit of related question on how much training data would you still require? So since you also called your talk data efficient algorithms, so did you validate? So how many samples can you go down that your algorithm can still generalize well? And did you also evaluate the generalization and extrapolation ability of your algorithm depending on your training data?
Yeah, so our training data M is 0, so the size of M is 0. The test data, you have only one test data. And this is your test data. This is what you're testing your algorithm on. And in terms of how sensitive your method is to the resolution, basically the number of points in your point cloud, these are the studies that we were doing. So this is really sensitive. 26 points in time and 500 points in space are enough to train this algorithm. So not only you are being data efficient here, so M is 0, the size of your point cloud, you're also being data efficient there. So 26 points in time and 500 points in space.
There's again a related question again to the data, and there is a question in the chat now. In the problems that we don't have concentration of the fluid flow, how can we solve the problem? We'll use which parameters, or how would you define the problem and formulate your architecture?
What was the first part of the question?
In problems where we don't have concentration because of the fluid or the flow, because you were using this information as for supervised learning, basically. So what if you're lacking even that information?
Yeah. So one way to know where you're on the landscape of what you can do and how much assumptions that you need to make and what type of method you need to come up with is to look at this arrow from left to right on your data. Everything with deep learning starts with the data. In our case, we had data on the concentration, so we had some data. We were landing somewhere on this arrow, and therefore you can make some assumptions about your system. Maybe you have some data on the concentration, and then you write down the equations for the concentration. Now the question is, what if you don't have data on the concentration? Then you're going to fall back here. Your data is even smaller. It means that you need to make more assumptions about your system. Maybe put some data on the boundary, and then that's going to be a forward problem for you. It means that you are doing a forward simulation. Given the inlet and the outlet, solve the forward problem. And actually, this is counterintuitive. The less data that you have and the more physics assumptions that you make, it's going to be harder to train your neural network. But the more data that you have, it's going to be much easier for it because it's going to pick up information from the data.
Thanks. I hope it did clarify the question, but if not, please feel free also to raise the hand and maybe you can ask the question again. There's also a question on the activation function, because you mentioned in your presentation kind of very shortly that ReLU did not work for you, or that you did not use it. But maybe you could explain why it did not work out for you, or also possibly why Tange activation function was a good choice for you.
Actually, to be honest, we are not using TANH. We are using this is the activation function. It's going to be x times sigmoid of x.
Okay.
And this is going to approximate ReLU. It's going to be a smooth approximation to your ReLU function. You need it to be smooth. People in deep learning can get away with ReLU because in the end, there is a summation over their data of a loss function for every single data point. And as soon as you do that summation, your function is going to end up being that's the one that you're minimizing, it's going to end up being very as smooth as possible. It's going to be.
Okay, thanks for this comment as well. There's another question. How do you build in constraints? And what if parameters for the constraints can only take values in a range? So how would you define those in the models and integrate them?
Yeah, that's a good question. And actually, you're going to need that for some problems. Maybe this Reynolds number, let's assume you want to let it train and learn it. And let's say you want your Reynolds number, you're looking for a Reynolds number in the range of 100 to 1000. You can put a tanh on that. It's going to be 100 plus tanh of a variable, maybe Reynolds hat, times 1000 minus 100. So these are the ways that you can enforce the range to be bounded, to be in a particular range.
Okay, thanks also for this clarification. There's another question in the chat again. So pins work in an unsupervised way. You can simulate. Now you starting from some GUI points, location, and time points, and get the corresponding solution. What are the performances of the method with respect to the number of input points in terms of generalization? To what extent neural networks help with respect to running the standard DNS?
I think the second part of the question I answered. It's that systematic study that I showed here with respect to the resolution and the noise. So you're being really robust with respect to noise and resolution. And the first part of the question is about, how about don't using deep learning, just using pure scientific computing to solve this problem. The problem there is that you don't know what is your inlet and outlet. It means that you need to keep back propagating your errors, adjusting your inlet and outlet. It means that you need to do thousands or millions of simulations to adjust your inlet and outlet boundary conditions to match this pattern. And each round of a forward simulation takes 48 hours. That number times even 1000 is a lot of days that you need to wait for the algorithm. This algorithm, on the other hand, is going to converge in 48 hours, the entire thing, matching this pattern. So basically, a patient comes in, we do CT scan or MRI on them, they go back home, they're going to come back 2 days later, and we're going to report the shear stress on the aneurysm.
There was a question from Luca Biccio, so possibly if the question was not answered, please unmute yourself and just if you'd like to clarify the question.
No, thanks. I think the question was answered. Thank you.
Okay. So thanks for that as well. There's another question. Can this method also be used to solve turbulent flows?
So the more complex you make this function, then you're going to need a deeper and wider neural network with more capacity. And at some point, I think we are not yet ready, given the sizes of our GPUs and TPUs. We are not ready yet to train a neural network that can approximate turbulent flows.
Okay, well, thanks for this answer as well. There's another question. As only point clouds are considered, there is no concept of context. Do you think graph networks are able to solve this problem, even if gradients are expensive?
So I'm not sure I understand the problem, the question.
You're not considering neighborhood in the concept or in the architecture. The question is if you believe that graph networks would support this additionally and would help to overcome some of the challenges that are faced by point clouds. But possibly the person who asked that could also clarify additionally.
Actually, now I understand the question. It's about which architecture are you going to end up using? Are you going to do 3D ConvNet, PointNet, graph neural networks? And to be honest, for this talk and this paper, we were trying to keep this part of the neural network very boring. We were trying to emphasize on the physics of the problem. But you're absolutely right. What if, rather than putting a point, you look at its neighborhoods and those be the inputs to your algorithm? Is that going to improve maybe the training time? Maybe it's going to improve the accuracy, your error rates. So that's a good point, and that's open for future research. And that's the idea of turning this gray box into something colorful, something more fancy, maybe DGCNN or PointNet or PointNet++.
Did you explore that a bit? Or are you currently, do you have something in the pipeline that where you're working on that?
Not yet, but that's really promising. Designing better architectures for the physics of the problem.
Okay, thanks for this clarification. I think at the very beginning, while you were still presenting, possibly it has already been clarified, but one participant asked if you could roughly explain what is meant by hidden physics versus actual physics, namely the first principles like conservation of mass and implicit physical models that are implicitly used. For example, the Navier-Stokes equation.
Yeah, so this is exactly the hidden physics of the problem. There is conservation of momentum. You express them in terms of partial differential equation, not their integral forms. And then there is going to be conservation of mass. And this is how you're going to represent them.
Okay. Possibly we could even stay on that slide because there are two questions that are going in that direction. So the present network would predict U, V, W based on the concentration into contrast due to colored dye. Can this be related to scalar advection of a passive tracer?
Yeah, exactly. So this concentration is a passive tracer. So it's tracing our flow. It's being advected by the flow and it has its own diffusivity. So some of the dye that we inject is going to diffuse faster, some of them are going to diffuse slower. And we don't actually want to make any assumptions of that. So you can actually learn the diffusivity of the dye that is being injected.
And there was a follow-up question. What if the fluid flow itself would change C during measurement? For example, change of contrast due to diffusion of dye or change of contrast in MRI due to flow?
Yeah, that could happen. Maybe you're measuring the temperature. And then the temperature is going to have some effect on the energy. Then there's going to be conservation of energy coming into Navier-Stokes. We haven't yet explored that again. When it comes to physics-informed neural networks, you can do contributions on what type of neural networks you want to choose and push the state of the art in that direction. You can think of your physics and consider more complex types of equations. You can study data, maybe more data, less data, data on different variables. You can think about the loss function. Maybe mean squared error is not the correct loss function to work with. Maybe there are better loss functions. So yeah, these are the directions. And
Okay.
and actually more complex geometries, more complex flow, like turbulent type of flows. So there is a lot of work to be done.
It's very true. There is a question in the chat again. Can we train this neural network in spherical coordinates?
In what? In a spherical coordinate? Yes.
Can we train this neural network in spherical coordinates?
Yes, absolutely. Then your equations are going to change, which should be fine.
Okay. Thanks for that as well. There's a last question on slide. Can you please explain the pixel conservation concept a bit deeper? Because the place is conserved, but the pixel values are not conserved. So how do you define this pixel conservation concept, and
Yes.
and how did it help you for this problem?
So that was just futuristic thinking of if you have conservation of pixel ideas, like what you have conservation of mass, then you can try to be a little bit more data efficient and maybe get away with the smaller models. But the idea is that the color of a pixel should not change from one frame to the other frame out of nowhere. I mean, a color shouldn't appear or disappear. It just gets transferred from one location to the other location. And in that case, you're going to get rid of these problems, like the short of this person changing color to be green. It shouldn't happen out of nowhere. And then you can write a differential equation for it. You first start with the integral form, and then you put you have some small area, and then you'd let that area to go to 0, and then you're going to get the partial differential equation for that.
Thanks for that. I think we answered all of the questions that were in the chat. Maybe some last questions, because you also mentioned trust and robustness. Do you believe that adding equations adds trust to the models, or how would you define trust in this case, and possibly how would you also present the information from these models to the main experts?
So I'm gonna trust this algorithm if I trust that mass is gonna conserve or momentum is gonna conserve. If I don't trust that, then I'm not gonna trust this algorithm. It means that I need to change my way of thinking. So the physics of the problem matters, and the physics is the one that is bringing the trust. Because whatever function that you're going to end up with here is going to satisfy those constraints that you put. And maybe your constraints are bad. Maybe Navier-Stokes is a bad equation. We don't know.
Also, did you evaluate a bit how much physics do you really need to add? Because, for example, you were mentioning the more complex the problem gets, and the less data you have, the more physical constraints you need to add there. Did you perform any thorough analysis on this? So kind of how much for which type of problems did you evaluate that, or did you focus on very specific problems where physics was already given? And then you did not face the question adding additional constraints and adding additional physics into the models.
So yeah, actually I have a paper here in the big data regime where you can actually, given enough data, learn your equations. And your equations could be in the form of a neural network, or it could be a linear combination of a bunch of simple functions. And the algorithm works. The framework is still this framework. You write on the loss function, you have some data, you have some equations, you try to minimize that. And it works. And you're right, in some of the cases, maybe you know your advection and diffusion. Maybe you don't know what is the correct reaction terms. those reactions you can actually learn from data. And that's going to be this case of data assimilation. So again, this arrow is really helpful. Just tell us where to land and what method to use, how much assumptions to make.
Okay, I think we're really well above the time, but I still wanted to finish the questions that were actually asked. There was one last question that was just asked. Once you introduce obstacles, the equations to solve are the same, but the pre-trained pins still be able to solve it, or does every change involve retraining?
Every change that you make, every new patient that comes in, there is going to be an optimization. So I wouldn't call this training because these are not your training data. That optimization is happening on when you're doing inference, when you're doing testing. So there is going to be some optimization when you do testing. But if you have data, if you have M, you can actually train this point net successfully, make it obey the laws of physics, maybe put some constraints there. Now, a new geometry is going to come in. You can just push it through this neural network once, and that's going to give you the corresponding flow. There is not going to be any need for optimization. So as soon as you have more data, then your life is going to be much easier.
Okay, thanks also. We don't have any questions. We don't have any raised hands as far as I can see. So thank you very much for taking the time, also for staying so long with us, even though we were planning to have it just for 1 hour. And thanks for sharing the results. And we are obviously looking forward to your new research results and to the new explorations you're going to add to the scientific community. Thank you very much.
Thank you.
Also for everyone
so
for
much.
staying.
Thank you so much for the invitation again.
Have a good day,
Thank you, everybody.
Maziar.
Yeah. Bye.